All right, this is the set of notes going over the states of matter, and so we'll be talking here mostly about solids and liquids and gas, but at the end I'll talk about some different states of matter or ways that matter can be interpreted. The first thing we start off here is a little puzzle, so maybe if you want to go ahead and read it and pause the video and see what you think, then I'll go ahead and talk about the answer to this. All right, so it's asking what's in the bubbles when something is boiling, and if you read it through, I'll just go ahead and tell you right away, the grandmother is the one that's correct. The bubbles are an invisible form of water. What that is water vapor, actually. The other answers are kind of interesting. The dads are kind of funny, because the dads is kind of funny because if it was heat, heat, if you remember from the last unit, is the transfer of thermal energy between a hot object and a cold object. So it seems weird that bubbles could contain the transfer of thermal energy between a hot object and a cold object. That almost doesn't make any sense to me. Kelvin here has said it's filled with air. That makes sense. These all kind of make some sense if you don't know the actual answer. But if it were filled with air, the question is, like, how does the air get down there to the bottom of the pot? The mom says they're empty. Well, if they're empty, the question is, like, why don't they just collapse on themselves if they're empty? That would be a vacuum in space, and so the bubble should just collapse. And then we've got Lucy here. A lot of people actually, when they read this, agree with Lucy. The problem with what Lucy says is if oxygen and hydrogen were coming out of water when it boiled, hydrogen is actually highly flammable. So what you'd have here is like a really impressive sort of tea kettle flamethrower as hydrogen and oxygen were escaping out of it. And it'd be especially dangerous if you had a gas stove because there'd be a flame nearby. And so luckily for us, hydrogen and oxygen do not decompose out of water when it's heated and boiled. Okay. So this talks about a simulation that we did in class. If you want to go ahead and do it online, you can search PhET simulation. It's PhET simulation on states of matter, and download it and experiment with it for yourself. But what we see here is as we're heating things up, it goes from a solid to a liquid to a gas. Solids have very nice organized shapes, and I'll show you a picture of that in a second, whereas liquids have variable shapes. They kind of conform to the bottom of whatever container they're in. And then gases will spread out to fill their container completely, and they're the most spread out. Water, I'll talk about also here in just a moment. So this is generally what they look like. As I said, solids, very organized, very simple structure. Liquids, they're moving faster, their particles are spread out, and then gases completely spread out. In fact, if they were in a beaker like is shown here, the gases would just completely shoot out of the beaker and go away. This is just another example of that, the same sorts of things, so you can read through that if you like and kind of try and see the ways that we contrast them. So the question is, like, what's happening here? And so what happens is there's an attractive force between these particles, which I talk more about in the phase changes notes. And as you add energy to them, the particles are vibrating more and more in place, because particles are never completely still unless you're at absolute zero temperature, which really nothing ever is at absolute zero temperature. It's the coldest you can get. It's a theoretical minimum, but one of the laws of thermodynamics says that nothing can actually get that cold. So we don't actually get to absolute zero, which means everything's at least vibrating in place. When you heat it up, it's vibrating faster. When it vibrates fast enough to give those particles a little wiggle room, it will become a liquid, it'll flow around. If you heat it up even further, it'll shoot all over the place, like a gas does. So that one question asked what was weird about water. Well, here's what's weird about water. When it's in its solid form, it actually is less dense or less compact than when it's in its liquid form. So if you remember, normally a solid is in this nice organized shape. Well, water is also kind of organized. It's organized into these hexagons mostly, and what happens here is because of the hydrogen bonding that's involved with water, the oxygens and hydrogens orient themselves towards each other in specific ways, and you get this really spread out sort of structure when it is a solid. And this actually goes to explain why ice floats on water. It's hard to imagine, but the world would be quite a different place if that weren't the case, because, say, for instance, if you're thinking about ponds, on the top of a pond during the winter we have ice, but below it is just unfrozen water, and the ice on top actually insulates the frozen water below so that fish can live and things like that. And so a lot of life originated from small pools of water and things like that, just microbes and things like that, and phytoplankton and protozoa and things, just in little bits of water. And if water froze and sunk, a lot more of the water on the earth would be frozen, and it would have made it less hospitable sort of for life to develop here. So again, some things here to think about. If we're talking about different substances, some that are solid at room temperature, some that are gas at room temperature, some that are liquid, the solids have the strongest attraction between particles. So that's why they're solid, even though they have the same temperature. For instance, if you're looking in a room and you have a room that has lots of nitrogen in it, and then it might have like a glass of water on a table, and then there's the table itself, which is a solid. 3 different states of matter, they're all the same temperature. So the question is, like, why is one a liquid, one's a solid, and one's a gas? It all has to do with the attractive forces between the particles, otherwise known as the intermolecular forces. And the more attraction there is, the more likely it is to be a solid at room temperature. The least attractive forces there are, the more likely it is to be a gas. So now we're going to get into reviewing about intermolecular forces and intramolecular forces. One thing to mention here is that the intramolecular forces are otherwise known as the bonds, and those are much, much stronger than the intermolecular forces. So when we boil a substance or when we melt it, we're moving the particles away from each other, which is overcoming these intermolecular forces, the attraction between molecules, but the bonds still stay in place. So when you boil water, it's not like it changes substances. It just changes state of matter. The particles move apart, but the atoms themselves are still bonded together. So intramolecular forces, the bonds, are much stronger than the intermolecular forces. So getting on to talking about intramolecular forces specifically, as I said, intra means within a molecule. These don't affect the state of matter. What they do affect is the identity, meaning that if we have atoms that are bonded in a certain way, it makes up different substances. That's how we know what substance we have. So H2O is a hydrogen bonded to 2 oxygens. It's water. That's what makes water water, is how the bonds form. But these don't affect state of matter, because state of matter has to do with the distribution of the particles. In a solid, they're close and compact and organized. In a liquid, they're spread out and moving around, kind of. In a gas, they're moving around all over the place, and they're spreading out completely. Intermolecular forces, then, we're going to get into talking about here. These are about the attraction between the molecules. So these do affect the state of matter. If there are stronger intermolecular forces, I said it's more likely to be a solid at room temperature. So these are what have to be overcome if we're changing phase. If we're going from a solid to a liquid, we have to overcome the attraction between the particles. If we're going from a liquid to a gas, we have to overcome that attraction between the particles. So phase changes really do involve intermolecular forces. There's more on this in the phase change notes, again, if you want to hear about that, about the relative strength of intermolecular forces, and when we're talking about solids and liquids and gases and heat of fusion, heat of vaporization, things like that. The other thing is, if it's got stronger forces, we're going to have higher boiling points and melting points, because we're going to have to get it to a higher temperature before that sort of thing, before they can boil or melt. All right, now I'm going to talk about these different types of intermolecular forces. The first one I'm going to talk about is the London dispersion force. This is the weakest type. It says it's the attraction between induced dipoles. Induced just means it's caused by or brought about by some usually outside thing. So an induced dipole is something that's created by being near something else that's a dipole as well. The thing that makes this weak is that they're temporary, and they're also due to the random motion of electrons. And I have a little bit of a diagram here I'll show you to help you see that. So what we have here is a normal atom. It's got some electrons spread around it, and those electrons move randomly around from place to place, and it just so happens that sometimes all the electrons move to one side of the molecule or the atom. If that's the case, then that molecule or atom becomes polarized just temporarily because the electrons are all on one side of it. And so this kind of shows you the step for how a dispersion interaction gets started. If we have two nonpolar molecules here, and then one of them has this random fluctuation of electrons, in this case the electrons congregate on this side of the molecule, it becomes polarized. And so this is a negative part, this side is positive, and it's near this other one. This is where the induced dipole comes in. So what happens is, because this part is positive, it attracts the electrons from the other molecule over to this side, and then this one becomes polarized. And now, as they're both polarized, they reach this quasi-stable state, this kind of stable state, where they'll stay for a while. But it's not a very strong interaction, and what can happen is that another particle will come in and it will knock them away from each other, and they'll both go back to being nonpolar particles. And so, as I said, it's a very weak sort of interaction. It's temporary, it's random, so that's that. The thing to keep in mind here with this one, though, is it has to do with the electrons, and so it's in everything. Everything has these dispersion forces, except for H+, which is hydrogen, which only normally has one electron, but if it's H+, it's lost that one electron, but everything else has it. So for all practical purposes, we're going to say everything has London dispersion forces. If you have higher molecular masses, you're going to have higher London dispersion forces. This should make sense because it has everything to do with the electrons, and the more electrons that you have, the more London dispersion forces are possible. This comes about in two ways. The first way is that there are larger atoms. Okay. The second way, so larger atoms, I guess I should say, if you're lower on the periodic table, you have more electrons, you have more protons, you have more everything. The second way is if you have a long chain of atoms linked together, so a really large molecule, you'll have lots of electrons involved in that as well. So looking at this, we're asking which one has the highest boiling point. The one that has the highest boiling point is going to have the strongest London dispersion forces. You should identify that then it's going to be the biggest one, because the biggest one has lots and lots of electrons involved in it, and so it has the potential for really high London dispersion forces. You can go ahead and look at those boiling points and see that there's actually quite a bit of variability there. So London dispersion forces, if you have a large molecule, can actually make a big difference. Moving on, we're going to talk about dipole-dipole forces. Dipole-dipole is attraction between polar molecules, and so this one would be things that are permanently polar. All right, so one side of the molecule is always positive and one side is always negative. This is different than the randomly caused polarity that came from the movement of electrons, because this is permanent, it's always happening. And so what happens is these two are attracted to each other, and it's just stronger because it's always happening. The third type we have here is hydrogen bonding. This is the strongest, and the reason that it's really strong, I'll show you here, is between hydrogen and when hydrogen is directly bonded to a nitrogen, an oxygen, or a fluorine. It's just a really strong form of it. It's why water has a really high boiling point, even though it's a relatively small molecule, and it also is why water has a high surface tension. The particles are attracted to each other, so like if you have like bugs, little water bugs that walk on water, the reason that their feet don't go through the water is because the water is really attracted to itself, and so it doesn't want to let those little bug feet in. And so kind of explaining how this happens with the hydrogen bonding, hydrogen, I said earlier, only has one electron. Oxygen, nitrogen, and fluorine are both really highly electronegative. Remember, electronegative means that they hog the electrons to themselves. And so if we've got this interaction here with hydrogen and oxygen, it's going to take that one and only electron that hydrogen has and hog it to itself, which means that the hydrogen is really positive, and the oxygen becomes really negative, relatively speaking. And so that's why hydrogen bonding is so intense, and why we give it its special class of intermolecular forces more than just the normal dipole-dipole interaction. Really though, hydrogen bonding is just a strong form of dipole-dipole. So looking at this, it asks which one has the highest boiling point. If you look at it, you'll see this one has no hydrogen bonding. This one has 2 hydrogen bonds, one between this oxygen and hydrogen, one here between this oxygen and hydrogen. This one only has 1 hydrogen bond here. And so the one that has the highest is this ethylene glycol here because it's got the 2 hydrogen bonds. So it's very, very strongly polarized. Now I'm going to talk about some other states of matter besides the solid, liquid, and gas. So the first one that comes to mind is plasma. It's the most common other form of matter here. What it is when you heat up a gas and the particles get going even faster, so fast that they leave their electrons behind, and so they become ionized, we say. And I think of this like in the cartoons where those people run away, like the characters of the cartoons run away, and they run away so fast that they leave their clothes behind or their shoes. It's exactly like that. So the particles are moving so fast that they're just stripped away of their electrons and then leave them behind. The next thing I'll talk about is a quasi-solid or a semi-solid or semi-liquid. The idea here is that not everything fits into a nice little box here. So sometimes things have properties of liquids and solids. So a quasi-solid is something normally that can support its own weight. It holds its shape. But it also conforms to what it's in if you put it under pressure, and it can flow. So the example I use is something like clay or Play-Doh. If you just set it on a table, like soft clay or Play-Doh, it's going to keep its shape. You know, it's not going to change that much just sitting on a table. But if you start pressing on it, it's going to really, really easily change what shape it is. And you can like put it through a tube. Think about those little Play-Doh machines with the crank that you turn and it like squirts out Play-Doh in a special like star shape or something like that. So that's just Play-Doh flowing like it was a liquid, even though it's kind of got other properties of solids. So we call those quasi-solid or semi-liquid. They're all the same thing. The last one I'm going to show you here is non-Newtonian fluids. These ones, what they do is they differ on how they move depending on what pressure they're under, and there are a lot of different forms of them. So here first are some examples. Cornstarch paste is really cool. If you put it under pressure, it becomes more like a solid. Other things like ketchup. Ketchup, when you put it under pressure, it actually becomes more liquid-like. So if you have a bunch of ketchup sitting on your plate, like a pile of ketchup, then you know it kind of stays in a similar shape. I mean, it's kind of liquidy. It's sort of a quasi-solid. But if you squeeze it, it really, really becomes liquidy. It flows very well when you squeeze ketchup, which is probably why we put it in a squirt bottle. There are other things that are similar. Quicksand is kind of solid when you're not moving around in it, but if you start moving around a lot, putting it under pressure, it becomes very liquidy. So if you ever get in quicksand, you don't want to move. And then, yeah, mud is similar. And gravy has cornstarch in it, so it's kind of like the cornstarch paste. There are some videos on YouTube that you might like. If you just type in non-Newtonian fluid on YouTube, you'll get a lot of different things. So you can see how those sorts of things behave.